Thanks, Neil and Elise. Hey, everybody. Thanks for having me today. Appreciate giving me some of your time. Um, the agenda shows 40 minutes of presentation, which I suppose is real. I do have a presentation, but I also want to prioritize having a conversation. So the last chunk of that presentation is there are some kind of topic areas and discussion prompts that I think might be productive places for us to spend some time talking. So, as noted, the presentation's recorded, the Q&A isn't. So maybe what I will do is I'll show those three, and then we'll go back up and we'll discuss, because I do want to have plenty of time to just have a conversation about this. This is some new stuff. Building grid integration is new enough that the answers are not all out there by any means. So I think this group might be a good source of info for me as well as for you. All right, with that, let's go in. So I've got this presentation put together. I will run through this. It's going to include some background on the topic, and then some pieces more specific to probably some of the work you're doing. So a couple of key themes on GridOptimal, just before we get started. One, building the grid is changing fast. There are regulatory drivers like renewable portfolio standards, right? Zero carbon grid by 2040 kind of stuff. There's also market drivers. Solar's really cheap. Batteries getting much cheaper, same wind, right? So there's a lot more, the economic case for distributed energy resources is getting better. At the same time as the building side regulatory pressures like energy codes have moved significantly, continue to move toward being more efficient and lower carbon. All that stuff put together and more factors means that there's pressure on energy markets and on utilities to do things like change their rate structures. So buildings are seeing more demand charges, more time of use rates coming in. Maybe they are now default, as in California, default time of use rates. So things like that are changing, and that in turn flows down from way up on the grid all the way down to oh, my camera's off. No, my camera's on. Okay, great. If you can see me, great. If you can't, I won't worry about it. That flows from way up on the grid all the way down through the utility to the building level. Buildings do account for 75% of all electricity consumption in the US and 80+% during peak hours. So the grid is really there to serve buildings. So all the things that happen on the grid really matter to the building. And then in turn, that matters to designers, because if there are going to be these big changes coming forward, then considering them before they happen is sort of a form of future proofing and not being left behind, fighting last year's war. So it's key to adapt to some of these changes on the grid, and that includes more interactivity as well as more focus on time of use and flexibility. And that's going to be important not just for making sure that rate risks are minimized, right? Keeping things affordable, but also making sure that buildings stay comfortable, that buildings are more resilient, that the grid itself is more resilient. And finally, like I said, 75% of all electricity use goes to buildings. We can't decarbonize the electrical grid if we don't also think about the role that buildings play in that grid. So I want to encourage folks to think of buildings as grid decarbonization enablers through their use of energy and the patterns that happen along those lines. So a note, NBI, we're a nonprofit organization, 25+ years old. Most of us sit in Oregon, but we have folks scattered around the country. And really, we have been working for decades to advance highly efficient, high performance, low carbon buildings to improve both the lives of people and environmental outcomes. So we're talking about moving markets towards zero carbon buildings, towards zero energy buildings, doing that in terms of advanced research, policy developments, market-facing guidance, market transformation. One thing we've been doing for some years is tracking zero energy buildings across the country. And in the decade or so, actually more than a decade now since we've been doing it, the first report came out in 2012, looking at the prior couple years. So in about a decade, we've seen 12x growth from 60, a couple dozen buildings really up to 720 some today. I just checked, and it's up in that region. So that's encouraging. You know, there are clearly many more than 720 buildings in this country, or in any tiny slice of it, right? But it's encouraging growth. And these are really the tip of the spear buildings, some very, very high performance, showing real leadership here. So it's encouraging to see this trend, and they are distributed throughout the country. California is, of course, very well represented, has been since the get-go, continues to be the leader in zero energy, but these buildings are all over, in every major climate zone, that is everywhere except northern Alaska, and in basically every building type you can think of, there's something represented. This map shows the verified and emerging commercial and multifamily buildings across the US. Now, if we were to succeed and get a whole lot more buildings to zero energy and fill this map with blue and green colors, it'd be awesome. However, what does that mean for the grid? So I like to think of there being a couple different flavors, if you will, of zero energy buildings. What's shown here, this is some work done on a real building by NREL and RMI a couple years back. The yellow or the golden shaded area is the building's load over one particular day. And then the green is solar PV production, so rooftop solar. And this is a day where the building netted out to zero. So its load goes, maybe this is actually annualized. I think it's annualized. The load goes up, 10 or 12 megawatts over the whole year. And it's over the course of the whole day. The area under the gold curve equals the area under the green line, right? That is to say it reaches net zero. The grid impact, however, in any particular hour is anything but zero. It's importing energy at night, it exports it all day long, and it imports again in the evening. So the building's peak, the PV isn't really doing very much to speak of to reduce that peak, maybe a bit, not a ton. However, the same building with now an enhanced focus on deep energy efficiency, on demand flexibility or demand response, can get to zero energy with a much smaller PV system. You can see that green curve is much, much lower. So first of all, that's less investment in PV, frees up more money for that energy efficiency to lower the curve. It's also changing the shape of the curve in part through that demand flexibility, moving the blue part over to better align with when the PV is available. So the net curve on the lower right, those peaks and troughs are much lower. So if we were to have a map full of buildings like this, where there are many thousands of Z&E buildings, it will be better as a society if we can make them look more like the one on the right than like the one on the left, right? The grid is not truly an infinite battery, even though sometimes we treat it like it is. That brings us to the GridOptimal Buildings Initiative. The idea, the central focus of GridOptimal has been to create new metrics to measure the quality of interactions between buildings and the grid, so across the meter. The intent here has been to create metrics that make sense to market-facing actors like designers, energy modelers, or building owners, architects, engineers, et cetera, and that still provide enough depth and complexity that they are truly useful to the utility on the other side of the meter. So the utility can have some confidence that says, yeah, if you get better according to this metric, we know you're gonna do pretty well. And that's actually going to help the grid in some measurable fashion. So we've put together a set of core metrics under GridOptimal. You can see there's some links here to a blog and a white paper, peer-reviewed conference paper that talks about what those are. Those also form the core of a LEED credit. So now you can get up to 3 LEED points for improving building grid integration using these metrics as a framework. The idea has been, well, we need some consistent and reasonably accurate way to measure this stuff. And then once you do, many doors open. So right now we're working on developing criteria for utility programs so that our utility partners, including those on the right and others, can use these metrics as a component of their utility programs. We're also putting together market-facing design guidance so that designers can get kind of an 80-20 look at what are some key things you need to do in certain building types or locations to improve the outcomes in terms of building grid integration. And then we're also taking this into code and policy realms, both in California and on the national model code front, and at the state level policy roadmap level too, actually, for that matter. And I should mention, GridOptimal is a joint initiative of NBI and US Green Building Council. And there are these supporting members on the right there, so much appreciated for their support. Thank you to all those supporters. But also there are several other organizations involved, folks like RMI and ASHRAE and so forth, national nonprofit organizations. So I guess I would say that's all pretty cool, but why do we even care about building grid integration and indeed getting buildings to zero carbon? Generally, there have been two basic reasons. Energy efficiency is often a metric or a goal, but it's been a long time since the US was actually low on energy. Back in the oil embargo in the 70s, maybe was about the last time, or somewhere in their 70s, 80s. Generally speaking, we're not low on energy. We are, in the last several years, we've often been the #1 oil producer in the entire world. It's not about having enough energy, it's about the implications of using that energy. And those mostly come in the form of carbon, so climate change impacts, and cost, or other environmental impacts as well, and cost. And that often is considered to be utility bill cost. I would add a third also. This is a picture from Louisiana from the recent hurricane from Ida of a utility transmission pylon that got toppled in the hurricane down there. And so it is not only important to consider what getting to a zero carbon building or a building with really good building grid integration means in terms of carbon impacts or emissions and cost implications, but also how resilient is that particular building, and does it contribute to or detract from the resilience of the overall grid? Okay, so with that in mind, that's kind of a picture of why do we even bother with this stuff, which I think is important to set the stage. So a couple of notes. As we move toward a grid with more renewables on it, and especially more variable renewables, wind, solar, whether that's utility scale or building sited, that is different parts of the US grid are evolving at different rates and are coming from different places as their baseline. So California has a significantly higher penetration of renewables in its grid mix than, say, Georgia or Alabama. Probably not news to anybody. So this is out of NREL, pulled out of NREL CalBEM. They've divided the US into 140 or so control zones or balancing areas to be able to say, here is the current and the predicted carbon implications of emissions at each hour of the year, today and out into the future to 2050 in each of these many zones. And as I noted, they're different. So CalBEM's got data on the state level, and we can talk about that as a data source in a little bit if we'd like to. Also at this more granular balancing area level. The point is that they're quite different and sometimes sort of surprisingly different, even though places may be right next door. The other consideration, as we get more variable renewable energy coming into the mix, is that it also varies, emissions factors also vary over time. So this shows 8,760 hours, all the hours in a year, of California's long-run marginal grid emissions. And you can see, this is 2020, what's showing here. You can see the green zone is relatively clean. So California's grid is quite clean during the day. In most of the year, it's a bit cleaner in the spring as well. You can see March, April, May, that there's kind of a green shading even overnight. But that the high carbon hours are often in the evening, especially summer evenings and overnight. Middle of the night stuff, right? That's when the sun is not shining. This is in part because California has a lot of solar on the grid. That's expected to intensify somewhat and shift a bit in the next 10 years and going forward. It's kind of hard to make these predictions, so NREL makes them. They actually make them out to 2050. I'm just showing 10 years out because there's there are plenty of both policy and market changes that I think make this a little hard to predict and be very exact about. In any case, you can basically see the pattern here, right? When there's a lot of solar on the grid in California, that translates to a relatively low grid carbon factor. Once the sun goes down, it gets things get dirtier. It's worth noting this doesn't necessarily align with the cost of power on the grid, and it also doesn't necessarily align with the total amount of demand on the grid or load on the grid, the megawatts. Those tend to happen in the early evening, but 3, 4, 5 p.m. is pretty high demand, even if it's still relatively clean because the sun is still up. So there are kind of different competing factors going on here that buildings end up getting exposed to and should respond to. There's the cost of getting that electricity, which has something to do with the total system load. And there's also the carbon implications of consuming that electricity, which is what's shown here. Okay, so great, this is neat and it's complicated and these graphs are fun to look at. I would like to get a bit more concrete about some of the actions that can be taken in a building to be able to take these factors into account, to try to maximize the use of relatively clean energy, minimize the use of relatively dirty energy, and do the same thing on cost. Maximize the use of low cost energy, minimize the use of high cost energy, and get to a point where the building is actively contributing to both grid decarbonization and to its own goals like minimizing utility cost, maximizing resiliency, that kind of stuff. So DOE, Department of Energy, Building Technologies Office came out with what they call their GEB roadmap. GEB is Grid Interactive Efficient Buildings. It's basically building grid integration. This came out in May of this year, and they include a couple categories of actions that a building could take. So efficiency is at the top there, right? So energy efficiency reduces power demand during all hours of the day. It's worth noting, this graphic shows efficiency reducing the demand equally during all the hours of the day. Not all efficiency measures do that. Their example measure is a tight envelope and a highly efficient HVAC system. That may actually have an outsized impact during those peak hours because relatively more of the building's demand is coming from HVAC during that time. So it does reduce hours during usage during all hours of the day, but maybe not exactly equally, which can be a good thing. And then we have load shedding, where you turn off a system. Lighting is a good example, right? You turn it off and it doesn't have any bounce back. Shifting load does tend to have a bounce back effect. So maybe thermal energy storage or battery energy storage can move load from one part of the day to another part of the day. And then there's modulate, also called shimmy in some cases. You've got shed, shift, shimmy. Let's not get too much into that. Batteries can modulate, smart inverters can modulate, but that's very, very short time frames. And then, of course, generate, on-site PV, for example, or exports from batteries from like vehicle to grid exports. DOE put efficiency first. I would postulate that efficiency comes first as not only the first place to look in terms of low cost opportunity, but also in our experience with zero energy buildings around the country, they are highly efficient, and the way they do that is first by minimizing loads, passive strategies, highly efficient systems, and then by layering the renewables on top. And the same paradigm applies for grid interactivity, that a highly efficient building tends to do better in terms of building grid integration. The median EUI for zero energy buildings across the country is 23, and this gray area is like the median 50%, so the middle two quartiles. As compared to a median office in 2012, CBEX, which is about 2009 year to 2010 or so, of 70, 65, 67, I think it was, much lower. And in California, the code is quite a bit tighter, so the median typical comparison performance is much lower UI, much more efficient. but still the ZE buildings come in quite a bit better. And that same paradigm applies for grid interactivity. So some of the measures that can help a building achieve that goal have to do with passive stuff, envelope, for example. And these tend to have a consistent or at least constant impact on the building's demand profile. It's load shaped, like that curve you see in the lower left. Day in, day out, passive measures are reducing the loads. They're relevant here, I think, also in that passive measures can be an impact multiplier. Passive measures and efficient measures can be impact multipliers for demand flexibility. So if you've got a super tight envelope and it's just hardly lets any heat in or out, you may be able to coast longer if you turn your HVAC system off or turn the fans down or the pumps down, something like that. It may be that it takes longer to, warm back up if you're in cooling mode, or vice versa in heating, because the envelope is so good. So it's efficient in and of itself, but it can also magnify the impacts from active flexibility strategies. I mean, you've got efficient building systems, right? HVAC, hot water, lighting, high performance systems. Plugs are also very important. And in fact, this second bullet, impacts during peak hours are often larger than off peak because more of the total load is from these systems. One example, we were poking around at the building grid implications of various different design and operations strategies, energy efficiency measures, and found, for instance, in medium offices that plug load energy efficiency almost blows everything else out of the water in some metrics, because the schedule is so closely aligned with grid peak conditions. So if you're trying to minimize your building's contribution to grid peaks, plugs are a great place to start because they tend to be pulling a lot of demand during those grid peak hours in a medium office. Not the same in every single building type, but that's an example of a permanently installed, like an appliance, a printer, say, permanently installed system that whose core energy efficiency can have an outsized impact on building grid integration. And then you make it smart, bonus on top of that. And then you've got active or flexible systems where things like batteries, thermal energy storage, managed EV charging can deliver flexibility, and not just those DERs, but also building controls on the mechanical system. So HVAC controls, for instance, can deliver more flexibility, which can then, be scheduled, or it can be ready to dispatch. And that's actually really important because I mentioned, here's the 2020 and here's the 2030 California grid carbon picture, those green and black heat maps. 2030 is a forecast, and I didn't even show 2040 and 50 because we really don't know that much about what is changing on the grid. We know the directions it's going, but just the fact that we have moderately good predictions, they're surprisingly good, really, I think, but those are predictions. One thing I know for sure is that the grid is evolving, and so flexibility is going to be more and more important. Exactly which directions it goes in are hard to predict, but I am confident of the increasing value of demand flexibility. So a couple, more concrete tips for design, especially in an environment like most of California. There are a couple things that are passive, right? So orientation, west-facing solar, west-facing shading, those both influence the building's net demand. So west-facing solar means relatively more of the production happens when the grid is peaking and relatively higher carbon. West-facing shading reduces building demand during those afternoon, summer peak hours and evening hours. And then a couple other pieces. I think smart inverters are straightforward. Communications capacity for basically anything that can take it is pretty important, and that enables that flexibility. So even if the utility doesn't have a program quite yet for some kind of DR 2.0 program, they're probably working on it, or if they're not now, they're about to be. So having the capacity to take a signal through something like OpenADR 2.0 compliant BMS system or heat pump water heaters with CTA 2045B compliant controllability. That's going to be important going forward, if not already. And then this thing about co-optimization, I think, is worth discussing. So a customer that says, I really want a battery and I want it for backup power. I want it for resiliency. I'm tired of these public safety power shutoffs, like the wildfire shutoffs, and I need to have a battery now. That battery may not be, in fact, delivering either cost or carbon savings if it's not dispatched to do so. But it probably could deliver both cost and carbon benefits if it were carefully dispatched with a focus on achieving both of those objectives. So considering these sort of multiple objectives of the systems is really important. And that applies to DER, distributed energy resources, DERs, like solar plus storage. It also applies to the building design itself in terms of core efficiency, passive strategies, mechanical system efficiency, renewables, et cetera, right? So trying to take into account all of these things up front, at least to some extent, setting a target on each has proven to be pretty important. And then finally, I mentioned plugs as an example in office buildings, but trying to find end uses whose schedules or whose intensity over time, over hours of the day, aligns well with high net load hours. And those are typically high cost, high carbon hours on the grid. In California, I should have put this graphic in here, but California, the California ISO integrated system operator has some pretty great graphics that show, today or any real day, real time load, total system load and net load patterns. So you can literally see the duck curve happening day by day. And we can pop over to that in the discussion if that's helpful. So we've gone through a bunch of research, multiple pilot projects, several large-scale modeling exercises, and we've done our own modeling. And in fact, Neil helped with some of that early on in GridOptimal. We've also leveraged modeling from several national labs, and we've got these sort of 80-20 type design guidance fact sheets where you don't have to go through all the metrics to figure out how they all work and go digging deep into this stuff. You don't need a PhD in electricity grid operations. What's the top 5 measures for office buildings or for buildings in California or the southwestern US in general, right? So those two cover sheets actually are design guidance fact sheets that are done. They've been sent over to the GridOptimal TAC for review. We're working through that system, and we expect to have about a dozen of these total, some on some on building type specific recommendations and some on regionally specific recommendations. And they should come out at the Get Into Zero Forum in New York City at the end of October. I mentioned early on that there is a lead credit. So just a note on that, there are three points available to project teams through a couple of different pathways. It is an alternate compliance path for the grid harmonization credit within the energy and atmosphere library, family, track. I forget what they call it. So there's 2 EA points and then 1 innovation and design point that you can get as this, it's called the GridOptimal Buildings ACP, Alternative Compliance Pathway. So first point, you basically calculate the building's performance using these GridOptimal metrics. I'm just realizing I don't have a table of them in this presentation, but I'll pull it up as we discuss. And then report. So there's a spreadsheet calculator. You put your 8760s from your energy model in baseline. You paste in the baseline. You paste in the proposed, and then the calculator spreadsheet kind of turns its little wheels, and you come out with the baseline performance and the proposed performance in terms of grid peak contribution, grid carbon alignment, short-term demand flexibility, long-term demand flexibility, et cetera. And I'll pull those up in a little bit here. So first point is make sure the baseline is the baseline to design is not making the situation worse, or if it does, then discuss, right? It's really just getting people thinking about this in the first place. That's the intent of the first point. And then there are 2 pathways to get up to 2 points, or 3 if you go farther. One is sort of the jack of all trades, relatively modest improvements in outcomes across multiple metrics, or across all the metrics if you want to really go deep. Or you can kind of focus in on one area in which you say, well, look, we're going to really nail it on aligning our building's load shape with the carbon profile on the grid, and we're going to improve that significantly. If you do so, then you can get 2 or up to 3 points. So it's basically a couple ways to do this. But honestly, there's 1 point almost free just for thinking about this topic and performing these calculations and doing a little exploring of it. And USGBC's explicit intent here is to get this started, to get designers to really start thinking about building grid integration and time of use energy efficiency, demand flexibility. So they're making this available to spark that a bit. Okay, so I mentioned that I've left a fair amount of time for discussion. I want to have the ability to spend some time talking about some of these things, and specifically in the context of energy modeling, what are the gaps? What can we do now? How do we model time of use energy efficiency strategies or demand flexibility strategies? How do we model them? How don't we model them? And then what would be kind of key gaps and key needs to start moving the ball forward on that? So in the interest of providing something for the recording, here's the first one I'm talking about. What are the accuracy barriers that are stopping us from accurately simulating these time of use impacts, either at the hourly level in an 8760, or in a more granular case, 15-minute is often is pretty typical for AMI, for smart meter infrastructure. So that's often used as well. The next topic is going to be, how can we better predict the ability of a building to deliver demand flexibility? And how do we say, yeah, this building's going to be able to shed 6 kilowatts in its peak condition? Can we do that in a model? Does that happen in a post process, et cetera? And then the third piece is the third piece actually gets to kind of that last sentence I said. Which things happen in the model inherently, and which pieces do we have to post process, and what's the right place to put those calculations? Should we truly model the implications of dispatching a thermal energy storage system and pre-cooling and so forth? Does that fit well in the model? Is it better post-processed? What about managed EV charging? Is that better post-processed? Because it just sort of layers on top, right? And then how do we actually do that? What are the inputs? What are the outputs? And what do they need to align with in terms of software or in terms of things like code compliance?